Tēnā koutou katoa. So I'm Claudine Stirling from the University of Otago, and I have two roles there. So one is as the Director of the Centre for Trace Element Analysis. So I work with a technical team, so there we are there just on the left, and we work together to produce trace element concentration data and also other data for lots of researchers on campus and also beyond the university as well, to support their research and their commercial projects. And then the other role that I have is an academic in the Department of Geology, and I'm an isotope geochemist. So what is an isotope geochemist? This is a little bit of a different kind of topic. So a geochemist would look at the distribution of the chemical elements and how they move within and between the different reservoirs on Earth, from the surface through to the deep interior of the Earth and back out again. And then an isotope geochemist takes us just a little bit further, where we look at each different forms of the same element, so heavy forms and light forms, isotopes. And they respond in a little bit more of a nuanced way when they move between all these different reservoirs. And so they can give an extra dimension of information for us, and taken together it tells us about the processes that have been going on through the Earth and even beyond Earth over time, over its 4.6 billion year history. So this is just a snapshot of the periodic table that you'll be familiar with. The circles are the different types of elements that I work on in terms of their isotopes, but today I just want to focus on one system, and that's to do with uranium and its isotopes. And that's because it's something that I've been working on for a long time, since I was a graduate student. I continue to work on it today, and it's something that I'm probably most well known for. So when we think about uranium, it doesn't have really good connotations, especially today. And when people think about uranium, they think about enriched uranium, and uranium that's been used to produce energy, both for nuclear weapons and also, well, nuclear energy for power. And that's nothing like what I'm talking about at all. So thankfully, I'm talking about natural uranium, which is all around us. People don't realize it, but it's everywhere. And so we can look at the natural properties, the geochemical properties, and also the radioactive properties of uranium. And it can tell us, provide a lot of really good information on the timescales that and the processes that have gone on through lots of different types of events that have taken place and shaped the Earth. So to give a little example, this is one of the main decay chains of natural uranium. We have this, what we call 238 uranium at the top of the chain. It decays slowly down to isotopes of lead at the bottom. It has a long half-life of 4.5 billion years, and by half-life I mean that it takes 4.5 billion years for half of that uranium to decay away. But I want to just point out these two isotopes here, another slightly lighter version of uranium with lower mass, and another daughter over here, or another isotope here that's part of this chain. Their half-lives are much, much shorter, so they're about 100,000 years, and it turns out that that's quite useful for us for looking at things like reconstructing climate change, for instance. So just if we have a look at this black curve here, this is a temperature record showing how temperature has changed over the last few 100,000 years, going from warm periods and cool periods and cycles of change. And what I've been interested in through part of my research in the past is looking at past warm periods. We're in a warm period today, so we can step back in time and look where these yellow highlighted areas tells us where we've had other warm periods. They can be viewed as analogous to global warming today. And therefore, if we can understand what's driving these periods, it might give us some information to put into climate models, for instance, for future climate projections. So I've had an interest looking closely at the link between sea level and temperature, and getting independent records for sea level based on fossil coral reefs. So this is an example of some reefs that formed during past warm periods. So here we have reefs 125,000 years old, 330,000 years old, and 630,000 years old. And we can get a nice indicator of where sea level was when the reef formed, and we can use those uranium isotopes to give us an age for the reefs. And if we put that information together, what we found was that it's quite likely when we look at these past warm periods, they tell us that probably it's quite likely that our current ice sheets are going to respond and melt if we have further warming, and going to contribute to a sea level rise, as we've heard earlier. So the other thing that we can talk about is innovations in technology that have been going on, in particular with new types of instrumentation. We can really open up the types of metals we can measure, and we can get really high precision information now, and that's really allowed some new fields to develop in this kind of area. So one, looking at the early solar system, so stepping back in time to the very start of the solar system, so 4.567 billion years ago, and trying to unravel the sequence of events that happened from what triggered the birth of the solar system, and how we went from dust to planets, and over what kind of time scales that happened. And these isotopes can come into play again, but this time, because we're looking so far back in time, it's the 4.5 billion year half-life of this parent and its ultimate daughter of lead, combined with another system, another isotope chain that can give us really high precision and high accuracy information on the sequence of events in the solar system. And an important thing is that we can now measure, we can link these chains together as is needed to be able to get an age for all these different events, because we can now measure this ratio that couldn't be done before. And it's revealing quite a quick timeline to go from very small particles up to planets of only a few million years or that kind of time frame. And then the final application I just want to touch on is that because we can now measure these two heads of those two different decay chains, which we couldn't before, it's showing us that there's quite a lot of variability in nature, and this is the sort of variations that we see when we look at samples that have formed on Earth's surface. And from looking at into this in more detail, most of these changes are due to oxidation and reduction reactions that go on Earth, and therefore they give us a link to oxygen state on Earth, and so therefore it gives us a tracer to be able to reconstruct the evolution of oxygen and how it's risen from nothing up to a big step change, and then another step change to the present day. So it means that we can look at these geological records, we can use this record, this ratio here, and we can track those oxygenation changes over time that couldn't be done before. So our work has been looking at calibrating and setting up those traces in modern ocean, in particular areas where there isn't any oxygen today. So that tells us how those isotopes are going to behave when they don't have oxygen compared to when they have oxygen like they do today. Black Sea has been quite an important study site for us. And then we can apply what we learn from looking at the modern ocean further back in time. And this is an example of applying this method to super greenhouse warming events. So really extreme warming events back at 93 million years ago. We can see these events in the geological record, usually as this kind of band of black material. And if we apply our tracer, which is really one of the only methods we have for trying to figure out what oxygen content was like, then we can see that there's a very close relationship between global warming and oxygen and weathering, global warming from volcanism. and we can actually quantify that there was quite substantial, like 50 times higher deoxygenation in the oceans then compared to today. So it kind of gives us a very extreme version of where things could go in the future if we were to push it this far and have extreme global warming. So that's another thing that we've been looking into. And I just wanted to finish quickly with some acknowledgements. I really would like to acknowledge the late Professor Keith Hunter for really wanting to invest in the types of techniques that we have set up at Otago, and for allowing me to come back to New Zealand as well. Also the technical team and all of the postdocs and students that we have as part of our group who have been really invaluable. All of the collaborators, and also I really wanted to acknowledge the Marsden Fund for the Royal Society, to Aparangi. It's been so important for me. I couldn't have done my research without it, and I'm extremely grateful to all of that, the support that I've had through the Royal Society. So I will leave it there. Thank you.
Thank you, Claudine, for that wonderful talk. I didn't realize that isotopic chemistry took you all over the world, all those fabulous countries. I have to rethink all Marsden stuff next time. So, are there any questions? I'm sure there are.
Thank you. That was a marvelous talk. If I remember rightly, you're assuming that time zero is the planetary creation. Is that right?
Time zero is the time when the first objects formed in the solar system.
In the solar system.
Yeah.
If you're looking at distributions of isotopes on Earth, do you have to worry about things like large asteroids or events like that where material from other parts of the universe have come and impacted on our planet?
It would depend on what you're looking at. So some of those signatures can be markers for impacts that have come in and impacted with Earth. So I'm thinking of things like potassium, for example. There's certain signatures that can be used to identify if we have an asteroid that's hit the Earth or not. It doesn't appear to be an issue for uranium. And certainly not when we look isotopically, because what we have on Earth today is a very well mixed planet, and actually the expectation for those two top of the decay chain, those two parent nuclides, is that when you measure the ratio between them, there wouldn't be any difference whatsoever, because uranium is a very heavy element and that would never happen. And so when I first started to see these variations, I sat on them for a long time because I thought I was wrong. I thought I'd done something wrong. Yeah.
Thank you.
We have time for one more question. If anyone would like to ask anything.
Thanks, Claudia. Are the half-lives of these isotopes the same if they're, depending on where they've ended up? Like if you're in some sedimentary rock compared to sort of, much harder types of substance, or
The half-lives are the same, no matter
where they are.
where you go through the whole solar system. No change there. So what matters is what isotopes in the decay chain are there at the time that the sample formed, and then what proportions are in there now, and then what biogeochemical processes have gone on to influence one isotope relative to another now. So we have to get a handle on all of that.